Hey, welcome back to Corey Ross. And this video will be used for 5 demonstrations. First, off of my 35 different demonstrations, it'd be number 1, the hammerhead. Video number 4 with the test tube up and the test tube down. Video 6 with bending the stirring rods. Video 7 with boiling water in a syringe. And video number 9 is using breaking open a lighter to show heat of vaporization, which is related to the one with the ice melt lab. That's a heat of fusion lab. So 5 demonstrations. First, hammerhead. My grandpa told me about this when I was a kid. I was trying to get the head on a hammer. You take the hammerhead and you point downward with the hammer handle, and you use the inertia of this not wanting to move to drive the hammer handle down into it. I've done this many different ways. This is the best. Don't hit this too hard. You'll never get that thing off of there. But if you just give it a tap, it'll be hard to sometimes get off there. So that's how to put it in there evenly so it stays using inertia. This was in my grandpa's high school physics book. He died in about 82 or 83. And he was an educated man at the time, because he had a high school diploma, but it was in his old high school physics book that my aunt gave to me. So pass that heritage on. That's what today's about for me. Number 4, test tube up and test tube down. Now, I'm going to dispute that humid air is less dense. That causality I'm going to dispute. I'm going to put it the other way around. Less dense air happens to be humid for weather mojo. I'm going to show you that humid air, the particles create a vapor, or come from a vapor. Okay, so I've got water in here. We'll fill 2 test tubes with water all the way. They're soaked. Dump them out. Give them the same treatment. Turn one right side up, turn one upside down, and tape them that way. And this will take a few hours. But if you tape them that way, I'll try to put it so I can see them with the camera. One will drain faster, will dry faster than the other. Now, if water is less dense than air, we should expect to see it rise up out of there. And that would dry first. If water is more dense than air, because I drained them both, then we should expect it to work its way out quicker. You can dispute this all you want, but I'm giving you a demonstration. Those water molecules weigh 18 grams per mole. In the air, oxygen is 32. 2 oxygens, O2 is 32 grams per mole. Nitrogen, 14 and 14 is 28. If you add all the 28s at 80%, all the 32s at 20%, roughly, about 1 particle in 5, the weighted average, the statistical measure weighted average for air is about 29 grams per mole. And you might say air's 18, that's less, it should float up out of there. But water's a vapor. It's a liquid at room temperature. When those molecules find one another in that air in there, they will get together in groups. And this has been research established. 2, 4, 20, a dozen, 50. And those clumped together water molecules that are coming and going, making those ultramicroscopic droplets of water molecules that are temporarily clinging together, those clumps have a mass of more than 29. And they will sink out of there quicker than they can float out of there, is my demonstration. That's video 4. Video 6 is stirring rods. When you are showing with a flame that glass is an amorphous solid and you can heat it up and it bends and doesn't crystalline, leave a little bend in there. That way your stirring rods don't roll. Or if you're making stirring rods and you round this in with heat and you round this heat in with heat, give it a little dipsy-do in the middle. You can still use it in a test tube to stir, but they don't roll off and break, and you don't have to make nearly as many stirring rods. That's video 7, or 6. Video 7 is boiling water in a syringe. If you put water in a syringe, and get all the air out and cap that and pull down, you will boil water in there at room temperature. Very little, because the pressure is low, so that water is going to fill a lot of space, so it'll be very little. Wouldn't take very much heat addition. You can also see bubbles going up. You're also pulling air out of solution. So if you do that a few times, you'll end up with a bubble in there that's mostly air. Get rid of that and you've got your air out of the solution and you're just dealing with water. But yeah, that's boiling water at room temperature. You lower the pressure, you get a water vapor pressure table, take it clear down to 0 pressure, 4 or 5 millimeters of mercury pressure, that you'll be well below room temperature. So you're literally boiling that and condensing it. Boil, condense. It's a heat of vaporization problem, but since there's so little liquid converted, it's not that much energy involved. And number 10 is a lighter. You can show the heat of vaporization with smashing a lighter with, this is sedimentary rock hammer. It looks an awful lot like a drywall hammer to me. Used it for hammering my hammerhead on. You smack the end of that with the pointed end, put a crack in it, you'll release pressure. Butane will boil out. It takes heat to boil that butane. This gets cold. It's a good demonstration of heat of vaporization. Like this. Out it comes, and it gets cold. It didn't have very much in this one, but it gets cold. You may want to have your vent hood on when it does that to pull air out of your room, because it makes a little bit of butane gas. Heat of vaporization. So there's those 5 demonstrations. That would be 1, 4, 6, 7, and 9.